My name is Bill Karwin. I'm going to be talking to you today about indexes. And where I'm coming from is Percona. We're a MySQL consulting and training company. We also make a few tools that we provide free of charge to the open source community, a version of MySQL with our own patches and enhancements, and a few other tools, backup tool and some query analysis tools. And I've been working there for about 2 years. Before that, I wrote a book. I wrote a book on SQL Antipatterns, and I'll show you a slide of that later on if you're interested. And prior to that, I worked for Zend. I was part of the project to do Zend Framework 1.0, and I worked a lot on the database component. So my background is definitely as a developer in PHP and other languages with a focus on databases. More recently, been focusing on query optimization and data modeling, doing a lot of consulting and training for Percona. So it's about performance. I've come to learn that presentations should always be about performance because that's the thing that's on most people's mind. So what I want to talk about is, as what I do, consulting and training, we do audits on MySQL database systems. What's the most frequent type of advice that we give to companies that are having problems with their performance? What's the easiest way to try to remedy those performance problems and fix things up without having to restructure your tables or make any changes to code? And yet, despite all this, what is the most neglected part of database optimization? And I'm going to say indexes. How many people have perfect indexes for all your applications that are running on your websites right now? I don't see any hands, unless you're all asleep. What do I see when I go out and try to do an audit for a company and assess their performance problems? What are the mistakes that I see? Or when I answer questions on the internet, I've answered a lot of questions on Stack Overflow and the MySQL forums and many other sites trying to help people optimize their queries. Here's one thing, probably heard this. I heard that indexes improve performance. So the more, the better. I'm going to index every single column in my database because I want to be prepared for anything. What's the problem with that? You may not need all those indexes. Only a subset of the indexes that are possible on your database are actually beneficial to your application. There is some overhead to storing all those indexes, both in disk storage and also in performance, because every time you change data, you have to update the indexed portion of that data. So it affects performance negatively during insert, update, and delete operations. And also, if you have too many indexes, it makes the optimizers work hard. The optimizer is part of MySQL and other database servers that analyzes your query when you execute it, decides which indexes to utilize, and then goes and executes it. If it has to choose between 100 indexes, it's going to have a much more complex job ahead of it. How many indexes would you actually need to index a table with n columns? Would you need n indexes? Would you need n times 10 indexes? It turns out you need n factorial indexes to completely index a table because you have the possibility for multi-column indexes and changing the order and so on. So it's impractical to index every single way that you could possibly do that. Indexes have overhead. Well, I don't want overhead. I want to minimize that, and so I'm going to get rid of all my indexes. But indexes are really beneficial and important to help speed up the queries that you have. Typically, in an application, you have more reads than writes against the database. You're going to be querying with select much more frequently than insert, update, and delete. So the overhead of doing the updating isn't so much of a problem. You want to have indexes to help the select. And in fact, the indexes help those updates and deletes as well when you have to make those changes against a subset of your data. This SQL is too complex. I'm just going to go with no SQL solutions because they just work after I create the right indexes. Because in NoSQL systems, MongoDB and CouchDB, et cetera, they also have the concept of indexes. And you have to generate those based on what is going to optimize your query load the most. So those have the concept of creating indexes too. You're not going to get away from the analysis required to create the right indexes by moving to NoSQL. In fact, here's trivia. SQL is an ANSI standard, ISO standard, as you probably know. It doesn't say anything about indexes. Indexes are left as a vendor implementation detail. And that is something that many people don't realize, despite the fact that statements like create index look very similar from one brand of database to another. It's not part of the standard at all. So if you want to use NoSQL, just use indexes. Then you could claim that you're in compliance with NoSQL. Here's another scenario. Here's my schema. They show a DDL script or a entity relationship diagram as I'm putting up on the background here. What indexes do I need? And that's a very frequent question I see online and at our customer sites when we do consulting. But in reality, you can't just look at the structure of the database and decide what indexes are the best ones. It really has to do with what your traffic is, what types of operations you need to do against those tables and columns, what types of joins and sorting and grouping do you need to do. So the right indexes are not something you can infer solely from the design. We have rules of normalization for relational databases that guide us on the best way to define tables and columns to store the data that we need to store. But what indexes are important, that's not covered by the rules of normalization or any other formal methods. So based on that, lesson number 1, relational schema design is based on data. That's the rules of normalization, first normal form, second normal form, et cetera. That's data modeling. But index design is based on queries. And this is the thing that I try to emphasize the most to sites. You can't get the right answers until you ask the right questions. Knowing your queries is important up front. So where do we get those queries? As we design our application, we can look at the code, but it may be easier to understand not only what queries are in the code, but how frequently they're being run and how expensive each query is. The sources of getting queries can be found in the database server itself in logs. My first choice is the slow query log. The slow query log is a feature of MySQL. I'm biased toward MySQL, but similar features exist in other brands. The slow query log shows you not only all the queries that are running, but also how long it took them to run. And that's important because you want to know, weighted by how expensive they were, which are the ones that are contributing to your load the most. The general query log shows you what queries ran, but it doesn't have any execution time statistics. You could also log in your application. You could have something layered into your database access layer that records which queries are running, how long it took them, and log that. But that is going to be only specific for that one application. What if you have other tools, ad hoc queries, reports, people writing other applications in other languages that are also putting load on the same database? It pays to have the log be managed at the database layer so that it accounts for all of those concurrent applications and tools. TCP dump. You could measure the actual Ethernet packets as they're flying around on the network and capture those on your database server, and you can estimate how many queries are running and how long it takes them. And that's a pretty good method, but generally the query logs are more complete and more precise. And I have binary log and process list on this list as well, but I have them crossed out. Why? Well, the binary log for MySQL users, you know that this accounts for all the changes to your database, but it doesn't include any selects. It doesn't include any of the read-only queries, so that would be an incomplete view. Also, the execution time statistics in that binary log are not very precise. Process list, you can get a sample of what queries are running at any instant in time by running show process list on a MySQL server or a similar command on other brands of database. But this is only capturing one instant in time. You wouldn't be able to get a complete list. Even if you ran this 10 times a second, you would still likely miss a lot of queries that are running in between those polling intervals. So let's focus on the slow query log. Enabling the slow query log on MySQL, you can use set global slow query log equals on, and that will enable that. It will start writing those to a log file. The log file will only capture those queries that are executing for a long time by default. the default threshold is, I think, 10 seconds. So it'll only capture queries that are extremely long running on the scale that we're talking about. You can change the threshold. You can change long query time and set that all the way down to 0 on modern versions of MySQL so that you can capture all the queries, whether they're running very briefly or for a long time. And that's important, and I'll show you why. And one of the features that we've implemented in Percona Server, our enhanced version of MySQL, is additional information to go into the log file. So you can get a lot of information about how it did joins, how it used the disk, whether it used temp tables, a lot of extra information that's very crucial for diagnosing what's the cause of certain inefficient queries. How do we look at this log file? There's a tool that we've developed at Percona. It's free. It's a GPL licensed free script that you can use to analyze that slow query log after you collect a good sample of your traffic. And it will give you a report and show you a list of the statements. I've included a link down at the bottom to the manual page so you can get information about that tool. I will be providing these slides online afterwards in the usual places. I have my own SlideShare account and whatever ZendCon is providing for slide sharing as well. So what does that report look like? Let me talk about this a little bit. Here's the usage of it. You can run PT query digest. You give the name of the log file as a command line argument and output that to just a text file where you can review the report. And I'll show you a sample of that report. It gives you a ranked list of where is your database load going. Of all the queries that it found in that log file, it totaled them all up, tried to group them by similar queries, and then gives you a total response time, the number of times that query was called, and the average response time per call, lots of other statistics. This is only a subset of the report. So I'll just call out a couple things. The number one query on this example was executed only a few times. Looks like only about 78 times, but the average execution took over 60 seconds per call. So this is definitely a very slow query. Versus another one further down the list, which was executed, 16,000 times. But each time it executed, it was very, very quick. And yet it made it into the top 10 because it was executed so frequently. So you want to know all this information so you can know which queries need to be optimized the most. You want to optimize where you're going to get best bang for your buck. How much could you possibly improve the overall site performance if you're focused on a query which is already accounting for less than 1% of your load versus spending your time optimizing one which is accounting for 28% of your load. Next, I wanted to talk at a higher level about indexes. A lot of talks that I go to about indexes spend all their time talking about the internals, about the nitty-gritty of how they implemented indexes and how it uses memory and so on. I'm going to try to do something a little bit different and talk to you about why indexes work at a logical level. And for that, I'm going to use an analogy to a telephone book. For those of you who haven't seen something like this, it's a paper book that has a list of everyone's phone numbers in a given area. It's organized by, sorted by last name first name last, and then associated with that line, it has the person's phone number. Right? Okay, so the syntax, if we treat this as an analogy to a MySQL database, would be that you would create an index, give it a name, on this table telephone book and specify the columns that you have in that index. Last name first name last, and then also include the phone number. So it's going to be sorted in those orders. All the Smiths together, because that's sorted first, and then likewise the first names and then the phone numbers. This is totally old hat to most of you, I'm assuming, but I just want to lay the groundwork. So if we can rely on the fact that this index is pre-sorted, this means that it benefits queries when we're searching for a particular value. And by benefit, I mean we have to search through a smaller portion, what they call an index slice, a subset of the data in order to find the ones that we're after. If we are searching for multiple columns in that, with an AND condition, combining the last name and the first name, we're looking for the Smiths, and then within the Smiths, we're looking for the John, people named John. So we get to narrow down the index slice even further. But, and this is where people ask me, does it matter what order I have those columns defined in the index? What if we search a telephone book, going back to our analogy, by first name? I want to find everybody named John in the telephone book. Well, the telephone book has the people named John scattered throughout the book. They're not all grouped together. So we actually have to search it cover to cover. We have to, we can't rely on the fact that it's sorted because we're not sorting on the last name at all. So order matters. Order of the columns in the index is important. We want to make sure that the conditions that we have start with the leftmost column in the index. We could create a second index on the same table with this, indexing the same data with first name first, last name second, and so on. And that would allow us to do that query, searching for the first name, and get the assistance of an index. But in the analogy with a telephone book, we only have one book, so we have to decide where we're going to sort it. You can use, if you had both indexes defined, you would be able to use either one of them to speed up a query if you had both conditions in your where clause. If you were searching for both last name and first name, either first name last or first name first would be usable in the same way. But only if we're searching for a single one or the other would it be important. Those are equalities. What about if we're searching for inequalities, what we call range comparisons? And what's a range comparison? It's when we're searching for multiple values in an indexed column. For example, using greater than, or between, or in, or like. So the predicate that we have in this where clause is going to match multiple values that are all going to be in that index. And in this telephone book analogy, we find all the people whose last name like S%, which is a wildcard matching, so that we find all the Smiths, all the Saunders, all the Stauntons, all the Shandlings, everybody who has the name beginning with S. If we extend that to also searching for first name, so everybody whose last name begins with S and then whose first name is John. But think of how you would find those in the telephone book. You'd find all the S's together, and that's good. The range comparison gets the benefit of that index, so you find all the S's. But then within the S's, you have a John here, a John here, a John here, a John here. They're not together anymore. So you can't narrow down the search any further. You have to effectively search all the S's to find those who are named John. And this is the principle that I want to talk about, which is order matters when you have range conditions in your SQL statement. As soon as you have a column on which you're doing a range comparison, the subsequent columns cannot be used for searches or sorting. And this extends to even longer indexes as well. So this is another reason why order matters in definitions of your indexes. When we want to sort by index, we can rely on the fact that it's sorted. Here's an example where we're searching for all the Smiths, and then we're going to ask for those to be returned back to the application in order by first name. When we have already narrowed down the index slice to those that are Smiths, we've already said, well, all the rows that are coming back are effectively tied with respect to the last name. They're all Smith. And then when they come back, we want them in order by the first name. Well, we know that the index structure already stores them in that order. So, and the SQL optimizer knows that too. So it can say, well, I don't need to do any sorting then. I can just fetch them back in the natural order that they're stored in the table or in the index. And voila, it's already in the order like that. So order by in this query is a no-op. It already knows that it's going to get the rows back in the correct order, so it can just move on. If you were sorting by something else, it would need to collect the results and then kind of hold the whole thing in one bundle and then sort them in place and then give it back to you. And that's the case where you're trying to sort by something which isn't the very next column after the one where you're searching by. If you're searching by the third column, or if you're searching sorting by the third column, or sorting by some other column that isn't in the index at all, you can't make use of that index for sorting, and it has to do it the hard way. So again, order matters. Which column you're sorting by should be the one immediately following that which you're searching by. And the next principle is index-only searches. If I am looking for the phone number, I know that I defined that index to include the phone number. It has the phone number associated with each last name, first name pair. It's already part of the entry that I'm going to get back, and therefore I don't need to do anything further. As opposed to a scenario where, say, we were looking up a business and we wanted to know their business hours, the business hours is not included in the columns of the index. We need to actually say, oh, well, I have the phone number. Now I have to call the business and ask them their business hours. It would be an extra step. And the inconvenience of doing that is actually very analogous to the fact of we can look up something in index and then subsequently have to actually look up the row of data to get the other column. Do you have a question? In the case of having the last name and the first name, where you put them in the where clause, if you change them to the other order, it doesn't matter because the optimizer knows how to do commutative operations with Boolean expressions. Okay, moving on. So columns matter. The concept that if we have the columns that we want to get back as a result set of the query in the index entry, even if those columns aren't being used for searching or sorting, it still benefits us. That's called a covering index. It means that our query doesn't have to do the extra work to go out to the other storage that has all the rest of the columns from that table, which could be another physical part of your database and would be expensive to go fetch. If it's already got it as part of the index, it's done. It's called a covering index in that way. And you can also hear the term index-only query. That is, this query is an index-only query because all the columns that it needs are contained in that one index that it's using. So all this background, this analogy, and the theory behind it gives us another lesson. We have a method to rate your indexes using what's called the star system. And I'm going to describe that. It comes out of a book called Relational Database Index Design and the Optimizers. I'm giving a link to it here in case you're interested in going out and getting that. Not a cheap book, by the way. But it's very well written, and the method is one of the methods in it is going to be covered today. So in the star system, it's just a way of organizing our efforts to try to attend to which columns need to be in the index and in what order. I'm going to assign 3 stars to a candidate index. 1 star is that I want columns that are in my search conditions, in the where clause, so that I can use them to effectively narrow down my search to the minimal index slice that is going to be the rows that I want to return from that query. The 2nd star is that I would really like to have an index that has the rows stored in the order that I want to sort by in the result of my query, so that I don't have to do any extra sorting once I get them back. Well, I wouldn't be doing the sorting. MySQL would be doing the sorting for me, but that's an expensive operation. I would rather it just fetch them off disk in the order that I want them already and then give them back to me. And the 3rd star is the covering index one. That is, any other columns that I need for this result set is also contained in the index. Let's see an example. Look at this terrible query. Well, the query isn't so bad. Query is a query. It describes a logical set in a certain order of rows in my database. The example that I'm using is based on the Internet Movie Database, IMDb. So here's a IMDb entry, cast info. It's who starred in what film. I want to get back entries that are starred for a given movie and a given role ID and give them back to me in the order in which they are credited in the cast. So what do I see in this? I see this is the output of MySQL's explain, which tells us how the optimizer is going to work with this query. This type equals all says that it's going to have to scan the whole table in order to find the entries that it isn't able to use any index at all to narrow down its search. It has to scan it cover to cover in the analogy of the phone book. Another clue is that it says key null. It hasn't elected any index to use to help it in this effort. And the fact that it's actually going to scan through 2.4 million rows in order to get that, or excuse me, 24 million rows in order to get that result set. And finally, once it gets the matching rows, it has to sort them by the column that we want it to sort by, and it has to do that in memory, hopefully in memory, maybe on disk, and that's going to be an extra bit of work to do. So how can we create an index to try to help this? Let's go to our star system. First, we look for the first star. We look for the columns that are in our where clause, the predicate that we are trying to search for. Since we have equality, they're both equality, and it's an and predicate, it's a pretty simple case. We just add those two columns, movie ID and role ID, to our index. Movie ID and role ID and become the first columns in the index. So that's going to give us the ability to narrow down the search and find the right index slice. The second star is the one for sorting. We want to make sure that of those rows of the index slice that we're looking for, they're already pre-sorted in the order that we want them back. So when we define the index, we add that extra column so that when there's a tie between rows of a given pair of values, the set of matching rows are already sorted. And then finally, a couple of extra columns that are not part of our sorting or searching criteria, but they're the ones that we want to get back as the columns in our select list for the result set of the query. So those, it doesn't matter what order you put them in, just put them at the end of the index. So those will be contained in each index entry, and they'll be returned without necessitating us to go and look at the table itself. Now, if we do the explain on the query, same exact query, so no code change happened. And no change to the structure of our table, just the definition of the index. We see now it is going to be looking up using this index that it's given a name movie ID to. Look at the rows. Instead of 24 million rows it has to scan through, now it only has to scan through 57. That's an estimate. Explain doesn't give you an absolutely precise number. It'll estimate that value, but it's going to be really close. The using file sort went away, so it doesn't have to sort this the hard way. It can rely on the natural storage of the rows in that index to be in the correct order that you want for this particular query. And then finally, using index tells us that it's going to get the covering index. This is the indication that MySQL's explain gives you that it's able to satisfy this query using the index alone, not having to read the table data. Win. Okay, so the star system is good, but there's some complications. There's some places where we can't always achieve all 3 stars in every case. Here's an example. If we have a condition in our where clause that has an or, they call that disjunction, and that is a case where we wouldn't be able to define any index that would satisfy that. Why? Well, think about it. If I'm searching for last name Smith or first name John, I can use an index with last name as the first column in the index to look up those Smiths. But then I also want any person named John anywhere in the database. So again, I'm going to have to scan through the whole database. Having an index with 2 columns doesn't help in that case. If I change the order of the columns, if I order the first name first, and I search for John first, I can find the John first, but then I also want or anybody named Smith anywhere in the database, which could be irrespective of any of the matches to John. They're not and, they're or. So there's no way to declare one index that can satisfy both of these. Therefore, you can't get that first star index. What about second star index, the one that helps us to sort without having to do that the hard way? Just like the range predicates spoil the use of the subsequent columns, they also spoil the use of sorting. If I find all the people whose first name begins with S, and then I sort by zip code, they're not together. The sort order of the index doesn't help me because there's some people in one zip code here, same zip code a few rows down, same zip code way down further. They're not bunched together, so the sort order of the index doesn't help. If I have a query that effectively does sorting by 2 things, like if I do a group by and an order by in different columns, that also spoils the possibility of having a second star index. Or if I am sorting by 2 columns that are in different tables that are joined together, there's no support for one index that spans tables, so you can't do that either. And also when you're doing a join, if I am fetching rows from the second table and I want to sort by them, I'm going to be fetching in a different order than the order that I'm going to be returning them. So that complicates things as well. So don't feel like you did something wrong if you can't find a second star index for your query. And the third star index, there are cases where this can't work either. The third star index is the covering index, which would give us the possibility of returning all the columns that we need for that query from the index itself. But there are limitations on the size of an index. In MySQL, for example, there's a possibility of only 16 columns per index. Can you imagine a query that uses more than 16 columns? Of course. What about very, very large columns like blobs and text and long varchars? There's also a restriction on an index width that you can only have 1,000 bytes in a given index entry. So if you have long string type of data types, you won't be able to create an index on them. MySQL supports what's called a prefix index, where you can say, I only want to index the first n characters, and you can declare what that is. But that's not going to give the whole content of that column. You could potentially have a column that's wider than those first n characters, and therefore it's going to have to go to the table itself to read those columns off of disk. So there's some cases where the third star also is unachievable for a given query. Let me show you another example of applying this technique. Here's a complex query, a couple of joins, and the nature of this query is we want to look up every actor who played James Bond, and again in our IMDb database. So we look up those who, character name James Bond, join that to the intermediate table for cast info, which says who played what character in what movie, and then further on join that to the actors' names. So that's how we're going to get that, and then sort by name. Look what happens when we do an explain on this. We haven't created any indexes to help us, so the first thing we see is that it's searching through all the character names. There are 2.4 million character names. And then for each of those, it has to scan through a 21.7 million row table, and therefore you multiply those two numbers together, and it actually is doing 52 trillion comparisons. This came up for me a few months ago. A customer called me up and they said, we have a query that's been running for all weekend for 72 hours. Help us optimize it. And it was a very similar case like this. No indexes, scanning through one multi-million row table, big intermediate table, and then a third table. So it was a very similar type of query. And their query had been running all weekend and showed no signs of stopping. So what can we do about this? We can find the first star index. That is, try to narrow down the search. We want to search for James Bond, put an index on the character name for James Bond. Note I use the prefix index syntax there, so I'm only indexing the first 20 characters. That should allow us to do that. It won't be a third star index because it can't get the whole length of that longer string, so it can't be a covering index, but it will at least allow us to look up the name much more quickly. And we can get a third star index on the middle table, the intermediate table for that many-to-many relationship, by putting the person role ID, which is the character in the movie, and the person ID together. So once we know James Bond, then we can look up all the matching rows of entries of playing James Bond in any movie, associated with that third star index principle, where you get the extra column for free as part of the index entry. Then that can be used to look up the corresponding entry in the actors table. And look what happens. We've improved the performance of the query by a factor of 480 million. So not too bad for a day's work. By which I mean it is able to find James Bond in the first table, and it says rows 1, so it's narrowed down the search to a single row instead of having to scan every single character in every movie. And then from there, it goes to the middle table, and it only has to scan through a much, much smaller set in that. Instead of 21 million, it's down to 100,000 or so. And then each one of those corresponds to one actor, so it's times 1 for the third table. Not too shabby. Question? good question. I'll repeat it for the audience. The question was about the or predicate. When I told you that if we have disjunction, you can't necessarily get a good index. It's true. You can't get a single good index that will do that. But there are possibilities of a query using 2 indexes and then finding the union between them. And there's possibilities in modern versions of MySQL that can do that. Some other database brands have that capability, but it's fairly expensive. It would be much better to have a single index that could narrow down the search much better. But yeah, there are cases where the optimizer can find the union or the intersection between 2 indexes and combine them in that way. Does that answer your question? Yes. Okay, thank you. Okay, so finally, I showed you the first star for one of those tables and a 3rd star for another table. Why can't we get the 2nd star? Remember, the 2nd star is about sorting. In this case, we don't necessarily know that the sort order of the primary key values, those numeric values, is the same order as the alphabetical order of the names of those actors. So we don't necessarily know that as we join to that table of actors and fetch back those rows, they will be naturally coming back in the order that we want them sorted. We do have to rely on MySQL to collect the results and then sort it itself and then give it back to us. So unfortunately, in this case, the optimizer cannot infer that it can get a 2nd star index at all. And that's not uncommon. Remember, I told you, don't be too upset. If you get 2 out of 3, that's not doing so bad. What about the overhead? Going back to one of the other principles, indexes cost overhead. Why do I want to store all these indexes? Well, we do want indexes that help us. We create the indexes that are going to be beneficial to the queries that you have. And remember, we talked about using tools to identify the queries that you have. And do away with or drop the indexes that are not helping you. How can we use some sort of automation or tools to find out which are the indexes that are not benefiting us? There's a couple of different tools. They're also made by us at Percona, also free, so you can feel free to use them. One is called Duplicate Key Checker. I have the PT is silent. Duplicate Key Checker analyzes your schema. Here's an example where I create a table foo, give it a couple columns, and then define a couple of indexes A and B, and then a compound index on the combination of A and B. I know, as an analyst, that any query that could benefit from the single column A index would also benefit from the 2-column index on AB. It would be just as beneficial to that. So I don't need both. And Duplicate Key Checker does this analysis for you. It'll go through all your indexes in all your tables and very quickly bring back a little report that says which indexes are the ones that you can drop, the ones that are redundant, either because they have too many columns or they are the same as the columns that are leftmost columns in another index, and a couple of other cases. It will also find redundant foreign key constraints and things like that. So it's very handy. And you can see the output here. At the bottom of the screen, it shows you an alter table statement. And after it's done the analysis and shown you its reasoning in the comments, it then gives you the literal syntax that would be necessary to drop that index. In theory, you could pipe this report directly into the MySQL client and it would affect those changes because it's valid SQL syntax. But I heartily recommend that you review it first so you agree with its recommendations. If nothing else, sometimes it takes a while to drop an index and you wouldn't want to do this on your production site without knowing what it's going to do. But it's handy to have the syntax already done for you. Okay, so that's indexes that are truly redundant, and we can get rid of those pretty freely. What about indexes that aren't redundant, but they are not useful either? Index usage is a tool that can help with that, to find unused indexes. In this, you need the context of the queries. The duplicate index was able to do its work without knowing what queries you want to run against it, but index usage needs to know the queries. We talked about this slow query log before that has that log of all the queries that have run on your system. Hopefully you've set that down to collect everything, at least for a sample of time. don't leave that long query time 0 all the time. It would make this log too large. But if I have a sample of my slow query log, I can process it through the index usage. What does this do? It runs the explain command for every query it finds in that log and analyzes which indexes those queries are going to use, compares that against the full set of indexes that are in your database altogether, and then reports to you those that weren't used by any query. And you can see that at the bottom. I have an example where it's identified an index and recommends to drop it, and tells you it's not a unique index, and that's in a comment. So it would have an output of there. This type of report is only as good as the log that you feed it. If you have a log which has an incomplete view of the indexes because you're filtering out all the quick running queries, it would recommend to drop indexes that are probably actually beneficial. So you need to make sure that your log has enough traffic in it that will represent all the usage of indexes. You might have jobs that run only at midnight, for example, that need indexes, but if you only collect the log at 2 p.m., you'd miss some of those. So again, review the output, make sure you know what it's going to do, and affect those changes. And I also showed that it does take some time to run this report. As it's going through, it looks like only about 1 minute and 7 seconds to run through this log in this case, but if you had a very, very large log file, it would take longer. Question? You're asking how much impact would this have to run this on a production environment? Yeah, it can be fairly expensive. So one trick you could do is don't run it on your production master. If you have a lesser used replication slave, you could run it there. It has the same data, and you can collect the logs on the master, move those logs physically over to the other server where it's going to have less impact, and then run the report there because it would give you the same answer given the same data size and the same indexes and everything. Does that answer your question? I'm sorry, can you speak up? That's why you collect the log. The replication server won't have the same select statements, but that's why you want to collect the log on your production master. The log is just a file. You can copy the file to another machine and then process it there. Okay. I'm sorry, I wasn't hearing all of your question. So the impact of actually collecting the logs, that can be somewhat expensive depending on how close you are to hitting the I/O capacity of your server. I've seen servers that are so busy that enabling the log actually puts a burden on the disks, so it's not able to serve the normal query load. And if you're at 90% capacity on your I/O bandwidth, then you want to be very, very careful about that. So what I do is collect those logs for a very limited period of time. In fact, I made a script that I can run the script, and it says, enable full logging for 60 seconds, and then turn it back to what it was before. And I'll do that, and so I can gauge how much am I collecting in the log for those 60 seconds. If I turn that on and suddenly I have 170 megabytes of log, I say, okay, that's enough. But if I turn it on and 60 seconds later I have 250 kilobytes of logs, I'm like, let's go for an hour. But you definitely gauge that based on how much your system is at capacity or not. Thanks for the question. Another source of knowing what indexes are actually being used on your system is if you're running our version of MySQL, the ones that we have enhanced, we've created some new dynamic tables in the information schema that give you that statistics. You can enable this. You can enable this by saying set global user stat equals on. This is only in Percona server, not in stock MySQL. It creates a new table in the information schema that you can query, and it'll tell you how many times. One of the columns is how many rows were read from a given index. It also has statistics for tables and users and things like that, but the one we're talking about for this purpose is indexes. It's a virtual table. The statistics are only maintained in memory anyway, so if you restart, it sets it all back to 0. And the nice thing is, based on our benchmarks, there is almost no impact to leaving this running. In fact, we've been talking about setting this on by default in our distribution of MySQL, so because the overhead of collecting these statistics, totally not high. You can use this by doing a join, like in this example, from the table that's simply called statistics, which is a standard information schema table which notes every index that exists in all your tables, joined to the new table, index statistics, that shows you which ones were actually being used since the last time you restarted MySQL. And I've showed this fancy query here, which is meant to only format the output as a series of alter table statements, so that like the index usage tool, it actually gives you the statements necessary to drop indexes that were never used. Pretty handy. And the final lesson is make it a habit. This is something that needs to be part of your operations as well as your development. So you need to repeat this query analysis periodically. Whenever you introduce new queries in your application or change a query to have some new terms in them, you may make it so that the old index was no longer beneficial and a new index needs to be created based on the techniques. If your site is very popular and you start growing more and more data, a query that used to run very quickly will now be slow because it doesn't have the right index, and will account for greater amounts of load on your website. So a query in that ranked list will change, it will go up or down based on how much data is in the tables. Or if the site traffic changes, if people are using your site differently, so they're hitting different pages which have a different set of database queries on them, that can affect which queries are accounting for the highest load. The Query Digest tool also has some flags for saving what it's analyzed before. So it'll actually write a list of all the different query fingerprints into a table. And then next week when you run the analysis again, you can say, well, I already saw these queries, I already reviewed them, so I'm going to mark them in this repository as having already been reviewed by me on such and such a date, and I did this in response. I can take notes and save them into the database. And then the next week, when I run the report, it'll be omitted from the new report. So you don't have to look at the same queries over and over again. You just want to see the ones that have changed, which is also a really good way of spotting queries that were never code reviewed. If somebody deployed a page with a new query and didn't go through analysis, you'll spot it the next time you run this because it won't have been included in the saved list from last week. And the query history saves not only the types of queries, but how they performed last week. So now you can compare them from week to week and say, oh, query number 7 is 20% slower this week, so we should maybe think about how we can optimize that or call out some data or whatever we need to do. Changing schemas may introduce new indexes. I've seen many sites where people had redundant indexes because they were created months apart and people didn't realize that they were creating redundant indexes. So running the duplicate key checker periodically after you change schemas or do migrations is worthwhile. The nice thing about duplicate key checker, you don't have to run it on your live instance at all. You could run it on a development instance because it's analyzing the schema itself, not the data. So that's very safe to do. You can do it on your laptop if you need to. And reviewing index usage or index statistics periodically to try to make sure you know which indexes are no longer used. Maybe somebody created an index for a given query, and then that query got taken out of the code, so the index to support that query is no longer needed. And doing this type of analysis on a regular basis can be very helpful. So the 4 lessons: identify your queries, use query logs, use the Query Digest tool to try to analyze that and make sure that you know which are accounting for the greatest load so that you know where to spend your time. Use a methodical approach to rate your indexes. The star system is one such approach to try to identify which columns and in what order you should have in your index definitions. tidy up by removing the indexes that are no longer beneficial or are redundant, and then adopt a process or a periodic job that you or your DBA are going to do on a regular basis to try to make sure that you have the right indexes for the query load that you have to make your site more efficient. I mentioned that I'm a trainer for Percona, and we have a new class that we've put together. It's an online class, and it covers a great deal of detail about that query digest tool that is part of our Percona toolkit. It's actually an online class. It's a virtual class. And so we're debuting that this month. And if you want to find out more about that, you can go to this URL. So that's something that's coming, and we'll be developing more specialized classes for the training department in the future as well. And I mentioned that I wrote a book, and I got my publisher to authorize a discount code. So if you're interested in my book, if you like the way I explain things, you can try to see my book about query analysis, database design, application design, and you can use the code ZendConSQL. I'm sure the capitalization matters, and you can get the print or the ebook through November 1st of this year. After that, it'll be done with. So that's my presentation about index. I hope you enjoyed it, learned something useful that you're dying to go back to your offices and try out. Any questions at this point? We have a few minutes. Yeah, question? Right, so queries that require hydration, so they're always going to be fetching select star. It's going to be fetching all the columns from the table, and because it has to populate member fields of an object. Whether you need those fields or not, the ORM layer doesn't know. So it always has to do that. Otherwise, you might erroneously think that the fields are... Right, yeah. In that case, when you do select star, it's very difficult to get that third star qualification to your index. It's very difficult to find those, unless your table only has a couple of columns to it. If you're pushing an index out to 15 or 16 columns, it's absolute limit, just so you can get that third star, you also have to keep in mind that that might be more costly than it's worth. I would do that only if that particular query were absolutely the one that I wanted to optimize for. That it was that was 97% of my load, and I really wanted to optimize that one query and get that 3-star index on it. But yeah, it would be a pretty tall order to say, oh yes, let's go for the covering index on a 15-column table. It's usually more costly than it's worth, just because storing the table with those 15 columns, then storing the index with the same 15 columns is going to use up a lot of your storage and memory. And memory, because at least in the case of MySQL, as you have an index, it's got to get loaded into memory just like data before you can actually utilize it. So the trade-off is storage and memory storage. So you want to be efficient and make sure the indexes are as compact as possible and yet serve the need. For that reason, the whole pattern of having select star be the de facto type of query in your application can be very costly. And what I tell people is use an ORM, do that hydration for the development time efficiency that it gives you. It helps you be productive as a developer. But then once you find a query that is becoming your bottleneck and needs to be optimized, you may have to unravel the ORM usage and do the query more specifically. Just fetch the columns that you need for that one occasion and do it by hand. In the same way that any programmer would say, I have this one hot spot in my code that I need to optimize very well, so I'm going to write it in C. Or a C programmer writes it in assembly. Or an assembly programmer writes it on the EEPROM, because it's something that needs to be optimized. So you can use ORMs for development time efficiency, use custom coding for runtime efficiency. Other question?
Can we go back briefly to the telephone analogy, telephone book analogy? Index, last name, first name, phone number.
Yes.
And then another index, first name, last name, phone number. To
Ah. Yeah, in fact, okay, so repeating your question, if you did have an or clause and you wanted to decide, should I create the index on first name, last name, or the index on last name, first name, and rely on MySQL's optimizer to do the union operation to try to give them benefit of both when it can. In general, that's not going to be as efficient as, the union and intersection, what's called index merge operations, are not as efficient as using a single index. So it would prefer to use a single index. A trick that some people use is do it in 2 queries. Get all the queries where last name is Smith, union, get all the queries, get all the rows where first name is John, and therefore the result comes back to you, but each of those component queries of the union overall query can use an index more effectively. So you can unravel an OR into multiple subqueries that are put together with union. And that's actually a pretty common pattern that I see, particularly for MySQL, which has this limitation on not being very good at using multiple indexes for a given query. Yeah. But it means that your query is now hard-coded to how many terms you have in it, and it gets, that's a trade-off of development time and how convenient it is to make any changes to that. Depends on what you want to optimize for, development time or runtime, just like the ORM problem. Another question? You? I'm sorry, can you speak up? I will be posting the slides. I put them up at slideshare.net/Bill Karwin, and I'll check with Zend to see if they have a repository just for this conference as well, and I'll participate with that wherever that is. And if there is, there should be instructions on their site or in their pamphlet. So yeah, I provide all my slides when I do presentations for under Creative Commons. You can feel free to use them or benefit from them. Any other questions? Otherwise, we can wrap up and we can go. Oh, you have a question?
How do programming functions on columns affect indexes? So it used to say select where, function on column.
Right. So the question is, how does it affect index usage if you apply a function to a column? If the function affects the collation order of the values that are getting back from the function, it won't work. It won't be able to use the index. So for example, I have a column which has dates in it, and I want to select just the ones from April. So I say where month, open paren, date column equals 4. It's going to come back. Those Aprils are not grouped together in the index. There's Aprils up here, there's Aprils in the next year, there's Aprils in the following year, there's Aprils in 2013. It's not going to be able to get a coherent index slice by applying that function. So it can be detrimental to the usage of that index to apply a function to a column. For that reason, you may actually need to store the month redundantly. You could store your whole date, and then you store an additional integer column for just the month and index that, if that type of a query is one you want to optimize for. If that's important for you to be able to optimize, it can be worth the redundant storage of that value in the second column just to get that indexed lookup. And that's a decision you have to make based on your application needs. In fact, what I say is any optimization needs to be done with that kind of judgment involved. And usually optimizations complicate your life. So you have to be frugal about how many of those you use, how many tricks you use, because it tends to complicate your code, complicates your database design, maintenance, et cetera. Yeah. Yeah, so if you're trying to do indexing to help you with calculating distances for geographical points, that's a whole difficult problem. because you not only do you have complex expressions using Haversine formula and distance formula and things like that, but you also have the fact that now you're doing range compare. If you try to do bounding boxes around them to try to narrow down your search, now you have, well, I'm going to do a between on the x's and a between on the y's. Remember I told you that once you do a range comparison on one column, the other column can't make use of the index. So you got to decide whether you have x's or y's. What I would recommend is look into Sphinx. Sphinx has really sophisticated support for multi-column indexing because it's a full text search engine, and it lends itself really well to geographical searches as well. When you have to do range comparisons on multiple columns, conventional B-tree indexes don't help you as much as other types of indexing data structures, and that's what is used in some other specialized search engines, and Sphinx has that capability. Cool, so it's time for the reception. I've taken you 2 minutes of your reception time away, so thank you very much for coming, and